I started.
Okay.
Hi everyone. We have machine learning using Python course module 5 session module 5 and part 3, which we term as session 9, which is session 9 of the 24th session. And I will hand over to Jamie Tsawa to focus on the part 3 of the module 5 for the classification problem, which he has been working on. Go ahead, Jamie, take over from here. He's the instructor who has been organizing this. And so let's give it to Jamie Osawa. Go ahead. Thank you very much.
So thank you. And hi, everyone. This is machine learning using Python classifications problems. And in this module 5.3, we'll be discussing about decision trees. This is session 9, which will be covering it. So the goals for session 9 would be the discussion about decision trees, building a decision tree classifier using the scikit-learn, then understanding the entropy or entropy and Gini criteria, displaying the trees that we have built, and also in the end optimizing the criteria or optimizing the whole tree in order to get the best of which trees, which with which hyperparameters and criteria the tree gives us the best results. So let's get started with decision trees first. So as we all know how a decision tree is made. So the decision tree starts with all of the data with the root node, and that depending on the condition, it is split into two parts, and those two parts are split into another two parts. In the image below, you can see that the root node, it has two child nodes represented by B and C, and then those those child nodes have their own child nodes where B and C become their parents to the child nodes of themselves. So D, E, F, G becomes their child nodes, and so on. So in the end, when when the further nodes are not produced or generated, it is called a leaf node. So this is just a general introduction to the decision tree. So let's just read out a few of the points. So decision tree, a model working resembles a tree, two trees where we have nodes as choices and branches with possible outcomes. Each data is classified until it is predicted with high accuracy and efficiency. A decision tree is a decision support hierarchical model that uses a tree-like model of decisions and their possible consequences, including chance event outcomes, resources, cost, and utility. It is one way to display an algorithm that only contains conditional control statements. Now, in the image, you can see that there is a one single tree, and also you can see that there are certain levels to that tree. Root node is level 0, then it increases from 1, 2, 3, 4. So those trees can be combined in order to make a forest called, and we call it random forest. That random forest can be used to make more accurate predictions, and those and a combined prediction is used as a result to the random forest. In this, we'll be only focusing on the decision tree, not random forest. So, we'll go through a few of the examples. So one is a decision tree being used as to represent a mathematical algorithm, mathematical expression, sorry, not algorithm, expression. So, and the tree is being split with the help of the mathematical operations or signs, you can say. Then comes the second example, which contains the event related to it. Then the third one, it contains a number of decision trees combined, and those and the predictions or the results that are given by those trees is uh, combined and on an average, which is the best result, is taken as the result for the whole collection of trees or random forest. So decision tree helps us with answering us yes/no questions if it's a binary classification. Decision trees can also be used for regression trees. So classification, we are discussing this under classification problems, and so we'll be using the binary classification tree. So a classification tree starts at root node having the whole data, further the creating subsets and splitting the data into multiple branches and creating child nodes based on different conditions to divide the data. This splitted data creates homogeneous groups of child nodes. Now, trees trees also help us to follow some of the business rules or generating business rules. And one of the reasons that trees are good is because it's easy to interpret the trees on what conditions they have spread the trees, and what are the other conditions for the being used to spread the tree, spread the data, sorry. So uh, classification and regression tree, as I just mentioned that the decision trees can be used for classification as well as regression purposes. They Here we'll be only using a classification tree. There is also a term called classification and regression tree called CART, which acts like an umbrella term. But when we use it for specific purposes, and the classification tree and regression tree are the terms that should be used. So what do? They measure the disorder or impurity in the data set, helping the algorithm decide the best feature to split on at each step. So basically, how decision trees can be split is, let's say there is a yes/no question, and further, if we actually predicted at random which are the yes and which are the no, the kind of disorder or impurity that we have in selecting or guessing that or predicting that which were the yes, actually yes, and which were the yes predicted as no and stuff. So those acts as an impurity. So that is why we will call it impurity and stuff. So splitting technique for the tree. A classification tree uses various impurity measures such as Gini impurity index and entropy to split the nodes. We will be further discussing about Gini impurity as well as entropy, and what are they and how they work. So regression tree, on the other hand, splits the node that minimizes the sum of squared errors. So decision tree is a supervised machine learning algorithm that can be used for classification as well as regression. So to generate a classification tree, start with the complete training data in the root node. Then we can use whichever impurity that we want to go with, we will be using scikit-learn's decision tree classifier, so which has a default value of Gini impurity, but we can use a entropy as well. So whichever we want to go for, then splitting the data, the train test module and stuff, the train test stuff that we have been doing. So the quality of splitting the data is very important during the training phase. When splitting, we choose to partition the data by the attribution that results in the smallest impurity of the new nodes. Then fourth is decide on the measure of impurity, that is either Gini or entropy. Search for a predictor variable that minimizes the impurity when the parent is split into child nodes. This happens when the original data is divided into two subsets using a predictor variable such that it results in maximum reduction in the impurity in the case of a discrete dependent variable, or maximum reduction in sum of square errors in the case of a continuous dependent variable, or for a regression case. Then we repeat step 2, which was for deciding the Gini or entropy for each subset of the data using the independent variables. All the dependent variables are exhausted. The stopping criteria are met. So few stopping criteria used are a number of levels of trees from the root node, minimum number of observations in parent or child node, and minimum reduction in impurity index. And the last is generate business rules for the leaf nodes of the tree. So as mentioned before, also we will be using the scikit-learn's decision tree classifier, and it takes a bunch of parameter values. We'll be using the criterion, which is a string value, which has default as Gini for the splitting technique, but we can use entropy. It takes a Gini or entropy as a value. Then comes the max depth, which is the maximum depth of the tree, and of course it's an integer value. Then comes the minimum sample split, and so the minimum number of samples required to split an internal node. If end, then the number of samples or then comes the in samples leaf, which is int or a float, the minimum number of samples required to be an leaf node. So as we know that how we are going to use the scikit-learn's decision tree classifier to make the tree, now we will be discussing about the data sets description. So there is the same data set that we have used in the previous session as well, which is for the uh, Portuguese banking system. Sorry, this is a German one. So German banking institution. So it has these various variables, and we used it. As you can see that the variable in the last variable, it has a status. So we used this data set to predict which are the bad credits from the uh, people, or which are the ones that can be predicted as a bad credit. So you can see that there are many categorical variables in this data set, which is a savings account. Then comes the present employee since. Then comes the personal status, the installment plans, checking account, job. These are all job, and status itself is a categorical variable. So which will help us to uh, spread the data, which can act as a condition to spread the data set for the tree. So uh, printing few of the column rows and columns from the data set. This is how the data set was, and these are how the values within look like. So we'll be splitting the data. So we have the credit df. We'll be splitting the data in the same way that we have used. So uh, from all this from amount to job, we'll be taking those as independent variables and giving it to uh, will be represented by x, and then the dependent variable, which is status, which will be used for the prediction, is our y. So, and the encoded credit df is nothing but the most significant variables collected into a single data frame, and those will be used to train the model. So we'll be splitting the data set for train and test purposes for x and y values. Then using the Gini criterion for making the decision tree. So we have the classification tree, which will be saving all the values for the decision tree classifier used to make the tree. Criterion is Gini, and the max depth we are given is 3. Then when we fit the data for the classification tree, the output is given something like this. Now you can see that it kind of summarizes for the values that we have given, or which it takes by default. So we have given the criteria for Gini. As you can see in the outputs first line, the criterion is Gini, then the max depth height is equals to 3. Now, measuring the test accuracy for the tree. So we'll be using the ROC AOC score that we have used in the past also. So the using the ROC AOC score on the tree that we have built, the score we get is 0.58. So as you remember, graphics and pi dot plus will be used, and which was mentioned before also for a visualization of the decision tree. Pi dot plus is nothing but a dependency which helps us to render the image. So now we'll be displaying the tree. So we use scikit-learn to, we basically will be using the graphics to use uh, which scikit-learn uses to make the decision tree, then pi.plus in order to use it in the Jupyter notebook. So you can, so the export graph is used. The first criteria is nothing but the tree that we have built. So we have built the CLF tree or classification tree. The output file should be named as a CSD tree.odt. ODT is the extension that will be used in order to convert that ODT file to the PNG file. Then the features name xtrain.columns, and the class names that we'll be using is a good credit and bad credit. Filled equals to true. Filled equals to true is nothing but a color used, and how color will be different shades of color will be signifying impurity, what amount of impurity is there and stuff. So for that, if filled equals to true argument is used. Then in the end, the graph is used using the p dot graph is dot graph from dot file. This is used in order to see the visualize the ODT file that has been created, and write.jpg helps us to create this image. And in the end, the import image that we have used while import statements, the that will help us to name the PNG file. So this is the a decision tree that we get. So you can see that the in the root node we have total 700 samples or observations, out of which 491 are good and the 209 are bad credit. And based on the checking accounts A14, if you remember checking account A14 in this description slide, you can see that in checkings account A14 means that uh, a person has no checking account. From A11 to A14, it lies for the different categories in the checking account for a different balance that a person has. The A14 and is a no checking account. So the decision tree is splitting the data based on no checking account, whether the person has checking account or not. And then based on that, the further classification is done using the duration, the installment plans and stuff. And you can see the Gini value or Gini impurities value for it, as well as the number of samples. And also the field equals to true, that was in class names over here. You can see the different shades of color signifying different things. So in the bottom left, you can see that Gini equals to 0, where uh, it's a blue colored node, and samples are 6. It's correctly classifying all of them as bad credit. So these are the kind of color variations that you can see. So some of the interpretations for this decision tree. At the top node, there are, as we have discussed, for the number of values, total values that it took, which was 700, and the Gini impurity index was a 0.419. Now, the the data at the root node, the data was split in terms of whether a person has checking accounts or not, and then uh, yeah, based on that, there were 425 samples that were used for not having checking account, and on the right side there were 275 samples in the, by the way, I'm talking about the second level. So there were 425 samples that that did not have the checking account, and 275 that had checking accounts. Then the nodes represented by darker shades depict good credits, while the nodes represented by light shades are bad credits. One of the rule can be interpreted as is if the customer does not have a checking account and the credit duration is less than 33 and does not have a savings account 65, then there is a high probability of being a bad credit. So there are total 70 records in the data set, and 48 of them are bad credits. So what I said uh, can be walked down like this. So go to the have your attention on the root node. So there is a checkings account A14, based on which whether they have it or not, they are spread. Then comes the duration. After duration, there is a savings account A65, which is also shaded as blue. So based on that, if if the duration is more than less than 33 and has a savings account A65, the there are total 70 records that are predicted as bad, and out of which 48 are actually bad credits. The same kind of uh, interpretation can also be said if the customer has a checkings account A14 and uh, in installment plans, which is A143, and age is more than 23, then it's a very high that it shows very high probability that the credit is going to be a good credit. So which goes for the rightmost side of the child node, where the Gini impurity is a 0.13. So these are the all the interpretations regarding the decision tree that we just said for this tree. Now let's understand what is Gini impurity and how it is calculated. So Gini is nothing but the summation of a probability of k into 1 minus probability of k. So it's the probability of a random sample being classified correctly if we randomly pick a label according to the distribution in a branch. Gini impurity can be computed by summing the probability pi of an item with label I being chosen times the probability 1 minus pi of a mistake in categorizing that item overall cases. If the impurity reaches 0, every one of the cases belong to the specific category. So we computed the Gini impurity using Gini node 1 and just translating this this formula into the uh, code. And when we print the Gini impurity, we get 0.149. 0.419. It was the Gini impurity of the root node, 0.419. Now, let's look at the other criteria that the decision tree classifier takes in as an input, which is entropy. So, so there are j classes total labeled from 1 to j. The entropy at node k is given by the formula minus into summation of from j equals to 1 to j p for j given k, and or the probability of j given k into log with the base of 2 for the j given k. So the value of entropy lies between 0 and 1, with a higher entropy indicating a higher impurity at the node. So when we use the same uh, same decision tree using the entropy, we are kind of getting the same uh, split and same kind of conditions being used in order to split the decision tree. As you remember, the decision tree started with the split of checking account A14, and based on duration and the installment plans, the second level of the tree was split. Sorry, the root node was split on the duration and the installment plans, and the second level was split on amount, present employed since, and residing since, and credit history, and so on. You can see that this time instead of Gini, it's entropy, and we are getting the 0.88 entropy. Now, as we move down, the entropy is no, sorry. Uh, so yeah, most of the tree that is constructed using the entropy as well as the Gini criteria, it's almost same. So some of the interpretations using the entropy criterion, the nodes represented by a dark shade depict a majority good credits, while the nodes represented by lighter shades are bad credits. This is the same as before. The rules generated at the top level nodes are same as the rules generated by the Gini index. Then the rules at the third nodes are different. Third level, sorry, are different, which is amount, present deployed since, residing since, and credit history, A34. So this was different from this. Here we have the amount, savings account, and age in the third level. Here we have amount, employment since, and residing since. So amount and residing since are one of the common ones in both the trees. One of the rules can be interpreted as if the customer has checking account A14, then installment plans of code A143 and the credit history as A34, then there is a high probability of being a good credit. There are 96 customers who satisfy this criteria, and 94 of them has good credits. You can see that in the rightmost side on the if we go from the root node has checking account, installment plans, then the credit history A34, and the entropy of 0.146. Samples, total samples are 96, and out of them 94 of them are good credits. So just like we calculated Gini, we will be calculating the entropy based on the formula that we have. So when we translate the formula looks something like that. As we'll be using the math module in order to get the logarithmic values, and the entropy value that we got is 0.88, which is at the root node over here. And when we test the accuracy using the AOC score or ROC AOC score, then the accuracy we get is 0.5763. So we would like to find the optimal criteria and the maximum depth. Basically, what we are trying to do is finding the most optimized tree for the criteria which we can give and the max depth. So scikit-learn's model selection has provides something called as grid search CV. So it which is a hyperparameter value as well as their most optimal values. So grid search CV needs to be provided with the accuracy measure to be used for searching for the optimal value. For classification model, ROC AOC values are used, and it uses k-fold cross validation to measure the accuracy. So the grid search CV, the CV resembles to this cross validation. So what is k-fold cross validation? So basically, let's say there is a data set. We are giving it the value of sorry, we are giving it a value of k equals to 5. So it will become 5-fold cross validation. So basically, the data set will be divided into 5 parts, and those 5 parts will be used for test and training purpose. So let's say there is the first iteration of using the data sets. So in the first iteration, let's say the first split, or say let's say fold 1, will be used for test, and the rest of them from 2 to 5 will be used for training purpose, and the same iteration will be going for all of them for a test, and then rest of them for training. So basically that's what a cross validation, a k-fold cross validation is. So grid search uses this. So grid search can be used for any machine learning model and can search through multiple hyperparameters of the model. It takes the following arguments, which is an estimator, which implements the estimator interface, parameter grid, dictionary with parameter names, which are strings as keys, and list of parameter settings to try as values. Then comes the scoring, which is our accuracy measure for ROC AOC score. Then comes the CV, is or the case value, how much we want to give it, and then configuring the grid search to search for optimal parameters, splitting criteria, Gini or entropy, maximum depth of trees ranging from 2 to 10. So this will give us the output in this term, the splitting criteria, which will be the most optimal splitting criteria, and the maximum depth needed for our tree. So we'll be going further with the k equals to 10-fold, k equals to 10, so 10-fold cross validation, and our parameter to measure will be ROC AOC score. So we'll be using the scikit-learn some model selection to import the grid search CV, then the tuned parameters. First was the criterion, which was for Gini and entropy. Then comes the max depth from range 2 to 10. And then the tree that we have used for the classification. So we'll be using the grid search CV and give that tree for as a parameter, first parameter value. Then comes the tune parameters. Then the CV equals to 10 as a case value as 10. Then scoring will be done on ROC AOCs. And when we fit the data for the CLF for the X train and Y train, will get this whole long output. But if we just sum it up, you can see in the last statement, it gives a criterion as Gini and max depth is 4 are the best criteria for our tree. So, so the benefits of using the decision tree, the tree benefits of building a decision tree classifiers are: rules generated are simple and interpretable. Trees can be visualized as well, and then works well with both numerical and categorical data, do not require data to be normalized or creation of dummy variables, and rules can help create business strategies. Based on the child nodes, the business strategies can also be implemented or can be learned from. So now we'll be going to look at the code. As you remember, we started with credit DF and the encoded credit DF, which are the most significant variables for the independent variables, and status will be used to be predicted. Splitting the data set for X train and Y train, and same for the test of x and y. Then using the decision tree classifier, the first tree that we made was on Gini, and the max depth we gave was 3, fitting the data. Now measuring the accuracy of the trees that we get, the first four we got was 0.58. Then for displaying the tree, as you remember, we used GraphViz, then for pi dot plus in order to visualize the image. So this was the tree that was used for Gini. As you can see that it's a 0.419, which was discussed in the slide as well. Then understanding Gini impurity, we implemented the Gini impurities formula in order to get it, and this is the output that we got. We got 0.4189. Then we built the same tree using the entropy as a criteria, and this was the tree that we get. When we calculated the entropy, 0.88 was the entropy that we got. So because of that, we tried to optimize our trees. Before that, the EUC accuracy score for the entropy tree that we built was 0.57. So from here, we started to optimize the trees. So using the gatefold cross validation, and the estimator used was the decision tree classifier. The parameters used was a criterion for Gini and entropy, and the max depth is 2 from 2 to 10. So the best score that was possible is 0.68, which is the ULC ROC score, and the parameters that we need is the Gini parameter, and the max depth we need in the tree is 4. So this was the session on decision tree, a quick intro to it, and a bit of optimization in the tree as well. So these were some of the resources used from the whole for the whole module 5. So yeah, this is it for the classification trees. Thank you.
Thank you, Jamit. To me, a bit of a understanding was that we have, besides decision tree, something else included in the module 5, I believe. That's okay. We can cover it under some other section or under some other session. So module 5, classification. What was the first one you took, and second one, what was the third one?
So the first one we introduced the binary classification. Then the second one was a gain and lift chart, and the third one was a decision tree.
Okay. So this is all about classification.
Yes.
And that is label based, and so it was all about discrete
Yes.
and logistic. So the logistic regression, which is part of the classification. So then once you did the classification, then you went into identifying how to measure uh, what is the gain or what is the lift that
Yes.
you give to boost. That is, how do you boost the convergence of the particular to optimize the predictions, right?
Yes.
So the classification was provided with all the measurements that you can provide the convergence, the accuracy, and all that. Now, this is a bit of a different thing because here you go ahead into. So, is it a unsorted data you get, or you get a sorted data? How do you get the data when you have the tree, binary tree here?
Yes.
Is your data unsorted, and so you are trying to
So whenever we build a tree, the tree will be built on a condition. So the algorithms will help build us the tree, and which will be the optimal tree further to split the data, as well as which will be the conditions in order to split the data in an optimal manner, which gives us the most better predictions as well. So the decision tree classifier helps us to do that and build the decision tree based on that.
so the impurity which you mentioned,
Yes,
specifically the Gini
yes.
and the entropy. Now, what does that signify essentially? Any interpretation you have for that?
Yes. So Gini, impurity, and entropy are the criteria based on which the split can happen in the decision tree. So almost. It is said that almost all the state-of-the-art algorithms uses Gini impurity as a default. Even in scikit-learn, the Gini impurity is good. Now, the reason for that is because computationally it's a bit faster to compute Gini impurity because it does not contain the logarithmic values. Now, the same goes if the on the other side, the entropy has logarithmic values, which becomes computationally bit heavy. So the entropies are not used, but though it doesn't mean that entropy cannot be just totally eliminated. Entropy can be used if you want to be very specific on getting a better spread. The entropy is told to get a slightly better split for the data for the decision trees.
So, is there any range for the Gini index?
Yeah, zero. Both of them, 0 to 1.
Okay.
If it's 0, it's a good model. If it's 1, closer to 1, it's bad.
So, essentially, there is a range of the probability. One has a log in it, one does not have a log in it, log to the base 2. So,
Yeah.
you are able to do on a logarithmic scale, whereas here it's a linear scale
Yes.
index. So, the division of the whatever the decision tree based on, and why is it called impurity? Any reason for that?
Yeah, impurity is basically so trees as also so trees are made on yes no questions in a classification thing. We can say we can introduce the trees in terms of yes no questions. So let's say that uh, there are 10 people, and out of 10 people uh, I am asking any question and also guessing that how many of them will say yes. So let's say there are actually 5 people who said yes, and I guessed 6 people or predicted 6 people to be telling yes. So that one can be said as an impurity. So
Okay.
in so the impurity is basically that not able to get the prediction right.
Okay.
So
So it is a question of your prediction versus a reality.
yeah,
So ground reality is what, whereas your prediction based on these indexes is what.
yeah,
What is the difference? And that is the errors.
y-
And
yes,
you have some. Mean square estimate for the logarithmic, that is for the entropy. And what about this one?
No, no. The it's for sum of squared error is for regression values, but
Okay,
we have only discussed on the binary
okay.
classification.
So this is binary, so it's
Yeah.
okay, well done. So what I would say is people still may have questions, and I just asked and recorded so that if they require any clarity, they can come back to you.
Sure.
In the meantime, of course, at the next session, are you going with the something you have already decided, or you are going to figure out?
So next will be learning about the on the uh, advanced concepts of the machine learning, but it will be based on what we have done till now. So it will be taking into taking the same kind of use cases that we have already discussed,
So the
and based on that, the cost functions and stuff will be done.
yeah, the basic thing is all just what I wanted to follow up is that as per the course we had said that we started with ML overview, went to the Python libraries for ML, then went into descriptive analytics, then went into probability distribution, hypothesis testing, linear regression, then we came to classification.
Yes.
So linear regression we covered, classification problems, binary logistic regression, and decision tree we have covered with all the measurements, etc. So the next is obviously it says decision tree and random forest models.
Yes.
So are you going to redo something for decision tree or just going with the random forest model? What do you plan?
No, the decision tree will be now, as the decision tree has been introduced. So the concept will be used or taken further with random forest as well, and the cost functions and optimizing the base ML models are uh, for the models that we have already created. What kind of optimization we can do for them. So it's based on that. So in a way, the modules 8 and 9 will be kind of going in complementary manner to each other.
Yeah, so you can cover part decision tree and the cost function which might
Yes.
same way you may do random forest and then do the optimization for that model, etc.
Yes.
So it's a bit of a mix. 8 and 9 will be mixed matching, so that you may do one followed by another, another followed by another. So they may be part of 8, 9
Yes.
together. That's
Yes.
okay. As long as you understand and people understand that you are covering a way so that it. So in the course till now, whatever is covered, if you go with the initial ML overview and Python libraries. So you have been using quite a bit of libraries, right? Most of the
Yes.
libraries. What are the kinds of libraries you used?
If just we have used scikit-learn, NumPy, pandas, then for visualization we have used matplotlib and seaborn.
So mainly the data frame Panda is the one which is the basic for most of the data capture, right? That means you are collecting some data from some place which is already cleaned up and all, and you bring it as part of the process and then work on the various models
Yes.
or whatever analysis you do or whatever probability distribution you work on. All that for everything you have got multiple data sets, and you have used different data sets like your IPL data set, your bank
Yes.
set, that is for the Portugal data set, which is for the again banking, and then Deutsche Mark data set. So you got global data sets, even including a couple of them for the stock markets you brought in.
Yes.
So what I'm observing is you have several data sets which you bring in from different places, and use them to do the descriptive analytics, probability distribution, hypothesis testing, linear regression, now classification. And now going forward, are you going to repeat, or you're going to get new data sets for the random forest models and all that, or is it still depends how you have you been using the same data set or something more than that?
Yeah, like today only we discussed the banking stuff with the same data set that we have used in the past. We
Okay.
have used the IPL data set 2 times, and also for learning the visualization stuff, we used the stock data set, stock markets data set.
So right now, until the cost function base ML models and optimizing the base models and the cost functions are over, you are not going to get into any uh, case study. You may still have clustering, you may have
Yes.
SVM or something is there. I don't know
Sorry?
where that SVM, some
No, SVM we are not covering.
okay, SVM. I think when you do clustering, take a look at maybe you can include SVM, maybe
Okay.
just so that we don't miss out, which is important.
Okay.
So while doing clustering, check if you have enough material, or can you split it into two parts. So not immediately,
Sure.
but what you have got 8 and 9 to cover, where you may not be covering SVM, right?
Yeah.
So in the clustering, you may include SVM. That's my opinion, and I leave it to you if you can,
Okay.
do it, so that you don't miss out on that, because a lot of people will ask that. Even though
Okay.
it's, you don't have to cover advanced, but you can do the basic of SVM. So 8, 9, again you are going flip-flopping in the sense that you may do decision tree followed by optimization, you may do random forest, and then optimization, and then maybe some other base models if you want to cover. In the clustering, probably you can, because you will be anyway distributing, right? So at
Yes.
that time, it might be worth looking at SVM. Does it make sense? And
Okay.
if it makes, include that. And then, of course, the case studies are there, and with the two case studies on forecasting and uh, recommendation system, we should wind up so that we can cover those things. So essentially, we've got another 1, 2, 3, 4, 5, and we have got we have covered now. Ninth is over, right? So
Yeah.
we've got another 5 weeks essentially, and so you can cover the every uh, part one, part two, maybe part three, maybe not part three,
Mm-hmm.
the remaining five, correct?
Yeah.
So see what you can do to accommodate best what you can, and
Okay.
obviously this will require some additional preparation from the beta testing we had done earlier. So this should be fine. I think people who are following, they will hear the record, hopefully understand that how we have been uh, following the uh, course
Yes.
objective, and they should be able to go through the recording and then get the, if they have done the recording, then the question is when they come to project, uh, they should be able to complete the project properly, correct?
Okay.
So, so I see 7 plus 5, you got 12. So that's good. So we are on track right now, correct?
Yeah.
Have a little bit in the end, we can try to do the projects when we have interactive sessions. Maybe we need to do some, make sure that people who are attending are following the certification, must at least join as a group, 1 or 2 people together, at least two, minimum of
Yeah.
2 person a group should join to be able to do, because then there is a teamwork, otherwise it's an individual work, right? So that's what we
Yes.
want to ensure that the teamwork is done. I think with that I will stop the recording. Excellent job, and hopefully
Yeah.
you keep continuing for another 5 weeks, 15, approximately 15, or
Yes.
whatever the number comes out to, maybe 14, I don't know. It's 24, right?
Yeah.
15 plus 9, 24. Yeah. Thank you.
Yeah.
So let me stop the recording.